Hello and welcome to this tutorial on lessons for building tensor product cubic B-splines. Note that we will focus on the lessons learned and not on programming the code. The dataset in use is the CFD results from Tony Sclafani of the Boeing Company for the spar section of the NASA trap wing at 6 degrees angle of attack. One lesson is in understanding how to add knots for the B-splines and when to stop adding knots. We add knots using dyadic intervals. This minimizes the number of knots for tensor product B-splines. There are multiple metrics that can be used for analyzing the approximation quality, for example the L2 norm or the infinity norm. Here we use the L2 norm because it does a good job of assessing the overall quality of the B-spline. Another lesson is the tolerance level for the employed error metric. Here the L2 norm. This seems to be more of a qualitative assessment. After building tensor product B-splines to panel code results from XFlyer 5 for the NACA 0021 wing, CFD simulations for a NACA 0021 wing, and CFD results for the NASA trap wing, it seems that the error level is both code and application dependent. In other words, a visual inspection of the results is required. A couple of ways to do this is by looking at each span-wise approximation, then the complete tensor product result, or looking at the residuals between the original dataset and the B-spline. We will look at both of these. I've already run the code, as can be seen here for the design point of Mach 0.2, 6 degrees angle of attack. My code prints out the span-wise location for every 5 nodes, and once all the span-wise locations are calculated, it goes through the rest of the coefficients. Let's look at the results. On the left, I will place the original CFD dataset, and on the right, the tensor product B-spline. So on our x-axis, we have our arc length, y, we have our span, or normalized span. The 0 for the span corresponds to the locations close to the body pod, and 1 near the wing tip. Arc length, 0 corresponds to the lower surface of the trailing edge, 0.5 near the leading edge, and 1 near the upper surface trailing edge. We have our CP value here. The same is true for the B-spline approximation. Just from a visual inspection, we can see that the B-spline does a pretty good job. We can rotate a little bit. We can see more of the pressure gradient near the leading edge. If we rotate the B-spline approximation, we see the same approximation level or gradient level. Alright, now let's look at the residuals, because the B-spline approximation looks pretty close to the original CFD. Let's see if the residuals can help us understand what is going on here. We'll place the residuals here on the right. Notice that the residuals have a wave-like or oscillatory pattern. This is because B-splines are cubic interpolators, and therefore the approximations are oscillatory. Our greatest error is near the trailing edge, near the wingtip, which corresponds to this location on the CFD. Arc length of about 1, span of about 1. If we look at that location for the CFD, there's a very high gradient, but we do not exactly know why there's a larger error there than here near the arc length value of 0, which would correspond to this location. Another point of interest is that many times the wingtip, which is this region here, tends to have a larger error than the rest of the body pod, or the rest of the wing, for instance near the body pod. You may notice, if looking at the error, that there are locations where the oscillations are more frequent, this is near the leading edge where there are larger pressure gradients. Therefore, more knots and control points are located here, so the oscillations become more frequent. Likewise, we have near the trailing edge on both upper and lower surfaces, we have more control points. Therefore, oscillations become more frequent. Depending on your application, your residual tolerance will change. Thanks for watching, and good luck coding.